So good evening. Welcome to the week 9 of Fundamentals of Additive Manufacturing Technology. So today we will be discussing on electron beam machining and additive manufacturing method, and the numericals of some related numericals of week 9 and some basic theory questions. So we will be proceeding. So I'll just start with the concept first. Okay. Okay. So in electron beam additive manufacturing, the material is supplied as we see in two different methods. Okay. And first is in the form of wire and one is in the form of powder. So here we see this is in the form of powder. Okay, I think some disturbance is coming. Can you please mute? Yeah. So this is in the schematic, this is in the form of powder. Okay, suppose if the material is in the form of wire, it has to be supplied in the form of external source. Like you can just take an example like this. This is a wire. And this is the electron beam. Just a second. Okay, sorry for the disturbance. Okay, so this is here wire is applied coaxially, and these are various different components in a electron beam additive manufacturing method. So okay, let's start with electron beam column. This generates beam of electrons. Okay, now in this type of additive manufacturing process, our source of power is high speed beam of electrons. Sorry, source of power is high speed beam of electrons. Now we can see that the mass of electron is equal to 9.1 into 10 to the power minus 31 kg, and charge is minus 1.6 into 10 to the power minus 19 coulombs. So this mass is very small, as we can see. Now, when this electron strikes on the powder particle or a substrate, it generates a lot of heat. Now, 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 how does this happen? If we have a small mass, kinetic energy is equal to half of mv square. So, this small mass, this will possible. This is like it may increase the velocity of the electron up to velocity of electron up to 2 by 3 of speed of light. So when the electron with this much speed strikes the surface, so with this much speed, it will generate a lot of heat. So we can summarize, or we can say that the energy which is getting generated is not because of the this is because of the high velocity. This is because of high velocity of the electrons. Okay, so this is a very important concept. So now next we will discuss about all these elements like filament, lens, and heat shield, vacuum chamber, electron beam. This we will discuss in the coming slide first, but this powder hopper we will discuss here. Okay, so I hope this part was very much clear to all of you. Now the portion which we have highlighted, electron beam, powder, start plate, this was also in your laser LPBF, laser powder bed fusion process. Now there's a what is the difference between in LPBF and EBM? So here vacuum is not there, we use inert gas. Inert gas, argon or nitrogen, but here we have vacuum. No need to supply any inert gas. So when we have vacuum, the properties of the final structure is much better as compared to the LPBF process. Of the final structure is much better as compared to the other. But again, since we have to maintain a vacuum, our cost increases to maintain vacuum. Okay, so this EBM system needs a high vacuum setup. And this is around 10 to the power minus 6 to 10 to the minus 7 bar. So for this thing we need a pump. So in your assignment also you have a question where it was asking which type of pump is required to generate a very low type of vacuum. So I think the answer will be the rotary. Okay, so this is one difference. So one more difference also. Yeah. One second. No, no, wait, let me check. No, yes. Mm-hmm. Yes. 10 to the how much? What is the data? Okay. Uh-huh. Millibars. Okay. I'll check that. Sure. Yeah. Mm-hmm. Mm-hmm. Okay. Yeah, sure. We'll discuss. Okay. Now in electron beam, the size of electrons are very small. Electrons are very small. So, so we need powder particle size is okay. So we need a powder particle size of bigger dia. Since the size of electrons are very small. Small. Now, this is generally 15 to 30 micron. Also may go to 60 to 90 micron also. Now, for this process, we know we need to take powder particles of bigger diameter. Now, because of this bigger dia, what will happen? The surface roughness is higher. So the surface roughness of EBM is higher as compared to LPBF. Of EBM higher than LPBF. This is one more major difference, and this is very important also. Okay, so these were the two main difference between EBM and LPBF. Now, next we will discuss about electron beam column. Now, in this we will discuss the electron emission methods. We have some questions and assignment related to this also. So, there are 5 methods: thermionic, photon, secondary, ferroelectric, and plasma. Commonly, we use only thermionic and plasma. This is the most common. Why it is common? This is more efficient method. Plasma is efficient than thermionic. Now we have some printers coming with plasma method also, but mostly we have with thermionic. Okay. Now we will discuss the principle behind all this. X beam printers come with plasma emission methods. Okay. Now this thermionic, this comes with Psyche, I think Psyche was the spelling. It is the company with Thermionic. Now in our assignment we have a question where what type of electron emission method uses the heat source. So it's very simple. Heat source is the thermionic. Thermionic method uses the heat source. So electron emission here occurs due to the heat supplied. We were supplying heat and electron emission is occurring. Now here, when the electron supplied is this and one is tantalum. And we, if you will be aware of this, we use this substrates metals in your FESEM, TEM, SEM. So when we supply heat, electrons start to emit, and these electrons will be only on remaining on the surface. They won't move to any other place. So we need some arrangement to focus or accelerate these electrons. So we will do this by applying voltage. Okay, so the concept is very short. Like it should be clear. We are applying heat, electrons are generated. So energy of the heat supplied is always more than the work function of the substrate. Substrates which we use are tungsten and tantalum, and these electrons are always on the surface. So we need a mechanism so that that will be focused. So there, this is the total gist of this process. Now, in this method, electron emission method, we supply photon energy. We are using photon. Now, these photon strikes on the substrate, electron emission occurs. In the third method, now this is written here heat, it is photon energy. Now, here you see so the electrons which we are using, those are the primary electrons and which were emitted. But since the method is secondary, then then we should be giving secondary electron rather than then the name should be primary. But still, if we will again go and check this, because I'm assuming that we are supplying secondary rather than primary, but still we'll go and check this.
Yeah, ma'am, it's
Mm-hmm. Yes. Yes, so I'm correct. So this is a mistake here. So I'm quite sure because we are supplying secondary electrons and the beam of emitting is primary. Okay. Yeah. Hmm. Yeah. Okay. Yeah. Correct. Now here we are using the fourth sense ferroelectric material. By using a ferroelectric material, here there is no heat. No external heat is provided. No external heat. So when we are supplying voltage, it has a tendency to, so we are applying a suitable polarity here. Now here we are applying a suitable polarity to control the transfer of electrons. Okay. So here the major thing is we are not supplying any external heat. Now, like we discussed here, in case of electron beam method, the velocity of the electron is 2 by 3 times of the speed of the light. Okay, so that is very high. So we have to provide a high voltage in this case. Okay, so the fifth one is the plasma. Plasma is positive ion of the electrons. Positive ions and electrons. Now here we have to separate this electrons from the plasma. Okay. Yeah. Separate this plasma and use the combination. So when we separate the plasma and use this combination, this is the plasma electron emission method, and this is the most common. You have to remember this. These are the most common. Now question is, how do we separate? By providing a suitable polarity. Suitable polarity. Now next we will discuss the thermionic gun. So this is the thermionic gun setup. So in thermionic gun we have the cathode, anode, focusing coil, deflection coil work. Okay. Now this is the setup of thermionic. Cathode is electron emitter. Tungsten or tantalum, which I also mentioned previously just now. So from the cathode, electron film on the surface, and we need to accelerate this electron. Now how we will do? And how we will do it? We will provide it through anode. Anode is positive, cathode is negative, and this will travel towards the cathode. Will travel towards the anode. So higher the voltage, higher will be the velocity. So here we will provide the high voltage, and with this we will control the velocity. Now problem arises that this beam consists only of electron. Now we know like charges will try to repel and unlike charges will attract. Okay. Now we will try to increase the velocity. Now when these group of electrons have same charge, they will try to repel. Now what will happen? this beam will try to diverge. Okay, now beam beam radius becomes high, and when it strikes the surface, it will not generate that much heat. Okay, beam radius, if it becomes high, when it strikes the surface, it won't generate that much heat. Okay, so we will use a focusing coil. So we use a focusing coil. This focusing coil which we use, it is a electromagnet. Now this is the electron magnet. Now this electron passes through the electron beam. Now you are seeing this electron is passing through the electron beam. Because of this magnetic field, force will act on the electrode. Okay. Now this will try to converge the beam. Deflection coil provides minor deflection. Now assignment question. With anode requires to pull electron from the cathode surface. Now this provides voltage. This is known as beam acceleration voltage. Acceleration voltage. So here in the bottom, this is the workpiece. So we know electron only strikes on the workpiece. So our workpiece should be conductive. If the workpiece is not conductive, then we have to do a coating, and this we usually do in the FECM process also. Okay, should be conductive. So this is another requirement, that electron beam process, we can only print metals because our workpiece needs to be conductive. Okay. When the metals which are not that much conductive, it's not possible to print with electron beam method. Okay. So this was about thermionic gun setup. Here is the numerical question. I'll come to that. Okay. One more thing I'll discuss here. In a laser beam, one more question was there. Laser beam, we have galvanometer. Now, in electron beam method, we use electromagnetic coil. Plasma method, shielding gas. is the summary which I am doing. Okay, this I think you will be clear till now. Okay, so now let's move on to some other questions. Yeah,
Just one more question.
yeah. Hmm. Uh, Not exactly. You cannot say corrects the shape. Like what is your exact point? Just can you elaborate? Hmm. It provides minor deflection. Yes. No. Which question number can you just tell me? Right. Let me check it. Okay. So now we will discuss some more questions. So for these are some straight questions. In powder bed based additive manufacturing process, which powder conveyance system is very common in agriculture and food industry. So this is which we have already in our slides also. It is like the correct answer is vibration. This is done to meter and transport granular materials. Okay. Now, in a powder feed unit, we have like metering, conveyance, and delivery. Again, in conveyance, we have some mechanical and pneumatic type of system. And there, under mechanical, we have vibration, screw, and gravity. Okay. So, next is which type of powder feeders are most popular for powder feed additive manufacturing and laser surface cladding? So, this is based on a pneumatic principle. Pneumatic principle here, it is done by creating a pressure difference uh, within the system by creating a pressure difference within a system. Now, this powder feed additive manufacturing, these are all commercially sold and they employ this pneumatic methods. Next is jamming is observed in which type of powder handling method in powder feed additive manufacturing method. So this you can because of jamming, use of gravity is uh, done as a method of powder handling. Okay, so this is gravity based methods. Next is in powder based additive manufacturing, which type of nozzles are preferred for powder delivery system to avoid anisotropy. So there are classification of powder delivery nozzles, classification of your powder delivery nozzles. This is lateral feed, continuous coaxial, discrete coaxial, central feed with annular laser, and this is central feed with discrete laser. So here the correct option is coaxial nozzles. Next is which type of nozzles are omnidirectional in powder feed based additive manufacturing. So lateral feed nozzles are not omnidirectional. Yeah, not omnidirectional. And this is coaxial nozzles are omnidirectional. So these coaxial nozzles, they are used in parts fabrication throughout the additive manufacturing process, while this lateral feed nozzles, they are used in cladding of rotary components. Fine. Rotary components. Okay. Yeah. Next is, which electron beam gun in EB based wire based additive manufacturing is affordable as compared to other. So this we already saw now also, the plasma gun. So why? Because plasma gun, we as we know, thermionic gun, we need to create vacuum, cost is more, we already discussed. So we have to create an entire low vacuum setup, which is costly. Plasma gun, we only need to supply electron beams to generate heat, and also it has a long life. Okay, one more thing I need to mention here. Thermionic gun and plasma gun, here it has a long life of greater than like 100 hours. This life is short life, around 50 hours. Okay, and this is less voltage, more current density, and here cost is more due to high vacuum setup required, due to vacuum setup requirement. This is more voltage and less current density. Okay, now the next one. What is the critical condition for metal transfer in electron beam based wire additive manufacturing? So there are two methods for metal transfer mode. One is droplet transfer, another is molten metal bridge. Okay. Now you in your this conditions, what is R, what is H? H is the critical radius for droplet, and sorry, R is the critical radius for droplet, and capital H is the height from which, yeah, droplet is coming from the filler material to the base metal. Droplet is coming from the filler material to the base metal. Now the critical condition is when this height is greater than or equal to twice of radius. Okay, next question. Why is rotation of substrate required in electron beam based metal? Now uh, electron beam based method has various challenges like residual stress and distortion, surface finish, need of support material, evaporation of alloying element material, and we have to maintain omnidirectionality, like that is dynamic adjustment of the substrate. So to fulfill this omnidirectionality, and so this rotation of substrate is required. So the correct option is this C, to maintain omnidirectionality and to maintain the consistency between the orientation of the vectors, that is rotation of substrate is carried on. This carried on. One now just I want to write it. Omnidirectionality is dynamic adjustment of the substrate. Next we will move to the numerical question. Fine. So this is your one of the assignment questions. I will just write the gist of this, how to approach and solve. So here we have been given a wire which has a diameter of 1.2 mm. Okay, and we have been asked to calculate the acceleration voltage in volts. Now we have been given current is 1 ampere. So, and rest all things are also given like density, Cp, melting point, room temperature, wire feed rate, latent heat of fusion. Now we know power is equal to voltage into current. Okay, this is one equation. The other equation is power required to melt the wire. This will be pi by 4 into d square into this is the feed rate Vf, okay, and into density into Cp melting point minus temperature, room temperature plus latent heat. This is your other equation. This is your equation 2. Now we have to find out equate 1 and 2. So by equating you will get this equation 1 V is equal to 1 by I pi by 4 d square into Vf into rho Cp Tm minus T naught plus L. Okay. Now so now you will substitute all the values. D is 1.2, Vf is to 2500 mm per minute, convert into seconds. Density it is given in kg per meter cube. So do the unit conversions properly, you will get the answer. And Cp is 468, it is given, and this is 1450 minus 25, and then your latent heat is kilojoule per kg, so convert it into joule, 260 to 10 to the power 3. Now divided by the and current it is given 1 ampere, so you don't need to do anything, just put all the values, you will get your answer. Okay, substitute all the values, you will get your answer. This is a very straightforward question. Okay, now this is a question of wire deposition. Okay, so before I'm going through this question, we will understand these 4 cases of wire deposition, what happens when dripping occurs, what is the smooth wire flow condition, what is the stubbing region. Okay, so for this we will just understand. See, in your x-axis and y-axis, you have in x-axis wire deposition volume per unit length of track, in y-axis you have energy per unit length of track. Okay, now this is the graph between energy versus heat rate. Graph is energy versus heat rate. Now you will be seeing that we have 4 conditions. Here in the first case you see your energy is high while your feed rate is less. Okay, feed rate is this I am talking meter cube per mm. So in the first case when dripping occurs, the feed rate of the wire is less and energy is more. Energy per unit length of track is more. Energy is more. So in this case, dripping occurs. So what is dripping? Dripping is wire is deposited in the form of drops. Like suppose this is the wires are deposited like here in the form of drops or beads are formed. These beads which is formed, these are discontinuous. So in this case, dripping occurs. Wire is deposited in the form of drops. Now, in the second case, where dripping may occur is written, may occur. That means feed rate is increased little, but still the energy is very high. Okay. Now, the third condition, which is smooth wire flow, this is the desirable case. Okay. Now, the last is where the stubbing may occur. It is the feed rate is very high, or feed rate is not very high, but we have less energy. Okay. Now, so to counter all these defects, we need a medium feed rate. See, suppose when your energy is very high, very less, when this is now I'm discussing the stubbing case. Okay. Now, in the stubbing case, what will happen? The wire will buckle when it will touch. Why? Because the feed rate is very high as compared to the energy, which is low. Now, what will happen? The wire is coming like this, like this, like this, and it will buckle. It won't sit straight on your substrate. Okay. Now, this wire will buckle when it will touch. Wire will buckle when it will touch. So for all these cases, we need a smooth wire flow. That is at a medium feed rate with a medium energy where there is no dripping or no stubbing. So two major defects which occurs when the energy and the feed rate when they are high and low, that is dripping and stubbing occurs. So we do not want dripping and stubbing. So we want a smooth wire flow, which will occur at a medium feed rate. You are seeing the feed rate is medium and your energy is also medium. So that is the condition which is required. Smooth wire flow. Now this I will write, wire is deposited in form of drops. Now here medium feed rate and medium energy. So in your question here it is given that you have a radius of wire of 0.7 mm and you have a leisure of power 1.7 kilowatt, transfer speed of 1.7 mm per second and a wire feed rate of 8 mm per second. So what will be the wire deposition characteristics will be? So here you will first calculate the energy per unit length. We have discussed this also previously, power by feed rate. This will be watt, this will be millimeter per second. Just put this value, power will be your 1.7 kilowatt and your feed rate 1.7 given. You will get a value that will be in joule per mm. Okay, now you have to find out your deposition volume per unit length. That formula is VL, deposition unit per length, VW by VT. Now A is pi by 4 d square. D you already know, pi by 4 1.4 square. See, VW by VT, wire feed rate and transfer speed, both are given. So you have to just put the value and get the answer. Okay, then you will get a value here. So from that you will confirm in the graph in what range it occurs. Okay, whether it occurs in this range, smooth wire flow range, so by knowing the range you will get to know your wire deposition characteristics, whether it is smooth wire flow or stubbing or dripping. By finding out the value, you will, when you get the answer, you will know it for sure. Okay, one more question is there which I have not discussed, like mentioned here. It is asked about the surface tension, okay, on the wire. Now surface tension on the wire, you will, how you will find out? You will find out by the formula for 2 pi r w sigma sine theta. What is this theta? Theta is the angle between the wire and substrate. Angle between wire and substrate. Now this, let me just check the question. This 2 pi radius is given as, I think this is 1, sigma you have to, it's not given, and theta is 30 degree, sine theta 30 degree, 1 by 2. So you will just find out and calculate, you'll get the answer. Okay, so I have discussed maximum questions from your assignment, and concepts also maximum is done. So I think this will be easy for you now. So you can ask if any more doubts are there. Like I'm done with the portion prepared for the class. So maximum concepts numericals we have discussed.
What the problem I told you about in Swayam.
Yes. They have
So
not
in the
uploaded the lecture.
notes, yeah. Lecture note itself, like sir's videos are there, but the related PDF slide is not there.
Yes, the slides are not there.
Yeah.
They're missing.
Okay.
Yeah,
Thank you.
anything else someone was asking? Yes.
Madam, can I ask assignment number 8?
Yes, sure.
In that assignment number 8, question number 10, madam.
Let me open it.
Okay.
So, but
That's
see,
only.
I'll suggest just write this. See, some people who are making the questions and people who are uploading and in the website, they are different. I think this is some you can put it up. Okay.
Another question, madam. Question number 13.
That videos also, I may think you will be cleared, but I'll just note this question just one second. Which is this 19. One more doubt also someone had, that one is 19 and other was what, that 8 4 pi by 3 10. Question number 10. And any other doubts from this? Has this assignment been evaluated for you guys? Okay. So the marks will be okay. Marks will be updated in this case. I think 4 pi by 3 needs to be changed because that's not the way mostly. And uh, this we did. This is solved last class, right? We got the answer, right? I solved it. Yeah. Uh-huh. Okay, okay. The class was not done. It was not done. Your range is from how much? I'll check this. 11. Yes. Nobody got 1228.6, right? This is a like this is not a fill in the blanks. This is the MCQ. Like four options are given, right? 1228.60, 600, 5200. No, no, it's okay. No need to type. But okay, this is you're saying there are MCQs. Okay, I did not check. Okay. Oh, you're saying this options are not given. You have to solve it, right? Okay. So for I haven't solved it. So you are saying the range is between 1000. Okay, I'll solve this. We'll solve this and solve this in next class, and I'll confirm with it final 1250. 1000 to 1250. Okay. 983. Yeah. Yeah. Okay, we'll check this. Okay, just I want to know this for this question. Your data is CPA is 480, melting temperature is 1800, room temperature 300, latent heat of melting is 2.7 into 10 to the power 5 joule per kg, right? Yeah, yeah. Question number 8. 8000 ml, 90%. Okay, fine. I'll check this with next class. Anything else? Any other doubts from these questions? Fine. I hope you will not face any problem in this coming assignment, assignment 9. Okay, this will try to solve. I think they have cross checked it everything. Yeah. Okay. 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 Thank you. Thank you all for attending the session. Let's meet again next week.